So metric system is what we'll be using here. So how do we report numbers? Like I said a while ago, this is one of the most important units of the year because this is how we're going to do our calculations. You know, so we have to learn how to report them. So first of all, there's no cussing in here. Okay, you can't use any of these four-letter words because these are all from the English system, foot, mile, all that. We're not allowed to use those. We're going to be using the metric system. Okay, and we never, ever, ever use the F word, Fahrenheit. Okay, we will be using Celsius and Kelvin. Okay, in this first unit, we'll do a couple of calculations to convert between Celsius and Fahrenheit, and that is just to give you a sense of how they relate. Because in America, we're one of the few countries that still reports temperature in Fahrenheit. But when we say it's 95 degrees outside, we know that's hot. But if you live in Europe and if they say it's 95 degrees outside, the world is ended. Okay, a 95 there is going to be a much lower temperature. We lived in Germany for a year, and I remember one time they were like, it's 32 degrees outside, and they were complaining about it being hot. And at first my brain was like, what? And then I was like, oh yeah, Celsius. So just so you can get a sense of that, okay? We also have no nudity in here. You may not put naked numbers down, or as I like to say, naked, as I'm from the South. I say naked, not naked. Use your units, okay? Because if you go into the lab and you said that it was 5, well, 5 what? Was it 5 degrees? Was it 5 meters, 5 grams, 5 milliliters? You have to tell me what that 5 means. It's meaningless without a unit, okay? Also, you are not Harry Potter. You are not magic. You can't just make a number appear. You must show your work. I want to be very clear about that. If you don't show your work, you don't get credit, okay? I know that some of this can be done in your head, but you need to show the process of how you got there, okay? And so please show your work. If I'm grading it and you don't have the work, it will be wrong, okay? If your work doesn't match your answer, then there's going to be some points off. But another reason you want to show your work, not just because you'll get it wrong, but let's say you set the problem up completely correct, and then whenever you got to the calculator, you transposed some numbers or you left a number out and you get the wrong answer. But if you have the work correct, you will get some partial credit, okay? Kind of like on the test yesterday, even though it wasn't math, you got partial credit for answers, okay? It wasn't all or nothing, okay? Although some of you it was. Nothing. No, just kidding. Don't want to scare you all. All right, scientific method. It is a process which researchers use to carry out their investigations. I don't know why I didn't do the red bullets there. I have to actually write this. In which they carry out their investigations, and it is a logical approach. So it has rhyme or reason to it. You don't just go in there and start throwing things together in the lab. You have to have a logical approach. Okay? I'm not even sure what happened to this slide. Do y'all even have that on yours? Because I changed the notes last year at the end of the year, and I think that I forgot to change this one slide. Do y'all have that slide? Yes. Okay, so that is okay. There was, I think of the next slide is where things changed, and mine wasn't matching up to what my notes had, and I was looking at last year's notes. Okay? So the problem solving, now in the crossword puzzle we did, there's a lot more components to the scientific method, but we're just doing the overall. Basically you state the problem, you make your observations, you develop your hypothesis, and that is the basis of carrying out your prediction. And then you perform your experiments to test the hypothesis. Okay? There's other steps, conclusions, all that stuff. If your data does not match your hypothesis, do you change your data? No, you change your hypothesis, and then you go test again. Okay? Very rarely does someone make a hypothesis and go test it one time, and bam, it's magic, it's happened. No, they are constantly, that's what research is. Research is constantly going through the scientific method process. Something doesn't match their hypothesis, so they think, let's change this, let's try this. And they spend years and years and years on research. I mean, think you all know that cancer research has been going on for decades. And some, in some cases they have found not a cure, but ways to treat it, and then some, it's really hard, and they're still working on that. There's some cancers that are more elusive in treatments. So that's what research is all about, is a scientific method. Eventually, after multiple experiments, the hypothesis, I can't say that today, could go on to become a theory. What is a theory, you ask? I shall tell you. A theory is universally accepted explanation of a problem. Theory should be constantly tested and challenged, and that should be and, not add, and may be refined or modified when there's new scientific evidence. Okay? They used to think that the world was flat, right? And then scientific evidence came out that no, it's not flat, now it's round. So they changed the theory that the world was flat. Okay? Although there are still some flat earthers out there that still think the earth is flat. Okay? I've not talked to one personally, I just know they're out there. Okay? Anybody a flat earther in here? Theories are different from laws. Laws state what general behavior observed to occur naturally. For example, the law of conservation of mass, which is the basis of chemistry, it's the backbone of chemistry, exists because it has consistently been observed over and over and over and over. There hasn't been any exceptions to it. Okay? It actually states that mass cannot be created or destroyed during an ordinary chemical reaction. Okay? And by ordinary, we're leaving out nuclear on that. Nuclear reactions aren't ordinary. Okay? There are two types of data, and I will tell you that on a test, children tend to get these backwards. And I don't know why, because there's some words in there that help you realize that. You have quantitative data and you have qualitative data. Quantitative data are things that you can measure. Okay, I can go in there and measure. They usually have a number and a unit. Okay, so things like temperature, mass, things that I can physically go and measure. Okay, qualitative is descriptive in nature. Okay, it's something I can observe, like color. Okay, the color of the solution is purple. I mixed two things together and it got warm. Okay, I can't measure. I could measure that, but I can sometimes tell just as much information. For instance, the Everything's Changing lab that y'all did. You could tell a chemical reaction happened by all of observations. We didn't measure anything. We measured out how much stuff to put in there, but that was so the reaction would happen in the correct parameters. Okay, but we said it got warmer. We didn't say how much warmer, but we know it got warmer, so there's an evidence. Okay, we said that we saw bubbles, evidence, right? And then we saw a color change. Okay, those would all be qualitative. Okay, so color, heat, that kind of thing. So, I mean, to me it's like pretty standard because qualitative has a quality, quantitative has a quantity, but for some reason on tests people get them exactly backwards. So I'm just giving you all a little word to the wise there. Okay? Any questions? So far so good? Pretty easy peasy? Now that brings us to scientific notation. Okay? So we're going to talk about how we do scientific notation. First of all, let me tell you, if you're going to use scientific notation for really, really big numbers and really, really small numbers, don't use them for normal numbers, okay? Some teachers do use them all the time, like use them for everything. I'm not going to have you put 105 in scientific notation. We can all realize that's a normal number and our brains recognize it very easy. But if you have a decimal that's got a lot of zeros in front of it, or you have a number with a lot of zeros behind it, we're going to put it in scientific notation, okay? So, basically, the way that works, for those of you that already know how to do it, just close your ears. For those of you who want a refresher, listen. Okay? If your number is greater than 1, your exponent will be positive. It makes sense. It's greater than 1, right? And you are going to move the decimal until there is one number, then the decimal. One number, then the decimal. And however many times you move the decimal, that becomes your exponent. Okay? So there's an example here. Let's just make up a number, 457. Now we'll do that many. We'll do 4,570,000. If I want to put that into scientific notation, if there's not a decimal there, I just assume, right? So I say 1, 2, 3, 4, 5, 6. So I would write that as 4.57 times 10 to the 6. because I moved it 6 times and it's a positive greater than 1 number, so it's going to be a positive exponent. If it is a number that is less than 1, then our exponent will be negative. Okay? So in this case, I moved it 1, 2, 3, 4 to get there, so it's 2.5 times 10 to the negative 4. Okay? So we'll do 1 or 2 examples. The homework that you picked up today, I don't know if you noticed up there, it said it's practice. Okay? Some of you know how to do scientific notation and you're great at it. You don't have to sit there and do the whole worksheet. But if it's something you want to practice and put it in correctly, then by all means practice it. And I'll have the key if you want to look and see if you did it right. Okay? But I did want to give you something. There's some practice in the notes, but some kids like more practice than others. So sometimes I'll give you things that are just for practice if you want to, you know. And I'll tell you if I'm either going to do a quiz over it or I'm going to take it up. If I say it's practice, it means you don't have to show it to me unless you just want to. So let's do number 1. I'm going to move that decimal to be 3.78 times 10. So I moved it 1, 2, 3, 4. So it would be to the 4th. Does everybody agree? So we're going to move, we'll do number 3. How many times do I need to move it? 6? 7.89 times 10 to the negative 6 because the number is less than 1. In order to go from scientific notation to standard, did I count it wrong?
Well, no, I was just asking how many significant digits do you want?
And how do you already know about significant digits? We haven't talked about it.
Well,
Oh, we're going to do significant digits later. So don't, for right now, don't worry about it.
okay.
Okay, I was like, most of the time in when they come to me, they've never heard of, we call them significant figures, but digits is correct as well. Most of the time, people don't know about that. So you're ahead of the ballgame. And typically, it's however many are significant, that's how many you include.
Okay.
Okay, but y'all don't know what's significant or not yet. So we'll talk about that. We actually learn this. We learn how to do the math, and then I tell you how to put it in scientific notation. Not scientific notation, sig figs. Because if I've tried it both ways. I've tried sig figs first, and then the calculations, and that bogs them down. So if I teach you how to do dimensional analysis first, and then say, okay, this is how we report it, it's usually a little bit easier. I've tried it both ways, and I have a little bit better success doing sig figs after. Okay. So to go the other way, to go from scientific notation back to standard, you just move the decimal whichever way, positive or negative. Again, if your exponent is positive, you're going to have a bigger number. You're going to have a larger than 1. So in this case, I would take 4.7. I would move it 4 times. 1, 2, 3, 4. And I'm going to fill in zeros wherever those little humps are. So that number would be 47,000. Okay. If I wanted to do number 4, I would say 2.9, and I'm going to move it 5 times. 1, 2, 3, 4, 5. So that would be 1, 2, 3, 4, 2, 9. So I fill in zeros. Okay. Again, you want to use these for really big numbers, really small numbers. Normal numbers, leave them like they are. 47,000 to me is a normal number. I can quickly look at it and see it's 47,000. Yeah.
So number 5, you wouldn't have us put that in the state.
No, I actually that's 957. So I would not have you put that. There are some science teachers that once you put everything in scientific notation, I feel like your brain can recognize 957 a lot quicker than 9.57 times 10 to the 2, right? But we're going to have numbers in here like, let's say, 1.2 times 10 to the negative 9 nanometers. You don't want to write 8 zeros in front of that. I don't want to count 8 zeros in front of that. If you start getting above more than about 3 zeros in front of a decimal, please put it in scientific notation. I don't want to have to count your zeros. I may miscount. You may miscount entering in the calculator. And if you put an extra 0 or not enough zeros, then you're off by a factor of 10. And then the answer's wrong. Let's think about money. If I'm off by a factor of 10, I can either owe you $100 or $1,000. You're going to be pretty mad at me if I owe you $1,000. I said, I'm just off by a factor of 10. It's close enough. Yeah. No. You just lost $900, you know. We're going to have some really big numbers. You'll learn this number. Just remember this. I'm showing it to you now. You will use this number a lot. 6.02 times 10 to the 23rd. Yeah. So do you want to enter all those zeros in? No, you do not. So that's why we use scientific notation. Okay? For the really big and the really small. What I call a normal number, leave it as normal. Yeah. Okay. So I'm just going to talk about SI units. I'm not going to talk about the metric system until tomorrow, but I do want to show you the SI units. Okay? Which was what the video that wasn't working was about today, is why it's important to have a system of measurements. So the international community in 1960, they adopted some standard measurements for our science things. Okay? So that when we're talking about an experiment, we're talking apples to apples and not apples to oranges. Okay? If I tell you that I was going, 75 kilometers per hour, and you don't know what a kilometer per hour is, you're going to be like, wow, she was speeding, when in fact it's not, it's not the same as going 55 miles or 75 miles per hour. So when we're talking science, we have these standard units. Okay? And then we add prefixes, which is the metric system. Okay? The metric system is very useful in that everything's by powers of 10, but we'll do the metric system tomorrow and convert with that. So I just want to talk about this real quick, and that there are actually 7 basic units that are defined by the SI system. We're only going to talk about these 5 because that's what we're going to be using in here. The other 2 are for physics, and we don't want to do that. Okay, you'll get them next year with Mr. McGowan. Okay. Mass is the SI, excuse me, the SI unit is the kilogram. I'm going to give you a little hint here. Every year on the test, lots of people miss it because they say it's the gram. Okay? And the reason they say it's the gram is because when we go into the lab, our scales, they're not scales. I'm sorry, science people. Their balances are in grams because those are smaller quantities that we can work with. Okay? But the SI accepted unit is a kilogram. Okay? Abbreviated kg. Length is meter, time is second. The amount of substance is the mole, and which was that 6.02 times 10 to the 23rd. That's a mole of something. And then temperature is Kelvin. How many of you have heard of Kelvin before? Okay. We tend to not measure in Kelvin. Our thermometers are going to be in Celsius, but it's a super easy conversion factor. Okay. The other one that gets people is, you see the abbreviation or the symbol for time? What is it? S. How do you normally abbreviate time? SEC. That gets them every year too. We do the symbol for time as S, not SEC. Okay. Now, if you're putting that on paper and you do SEC, I'm not going to count that wrong as a unit. But on a test, if I'm asking you what is the proper abbreviation, and you put SEC, you're going to get it wrong. So I've made note of that, and every year I make note of it, and people still miss it.
And then for the temperature,
well, the temperature is a lot of times we use Celsius, but when the really only time we're really directly working with temperature as a measurement or as a value is when we get to the gas laws next semester, and the temperature has to be in Kelvin to be able to use the gas laws. But that's next semester. We'll worry about that later. But it truly is the easiest conversion, because to convert from Celsius to Kelvin, you're going to add 273. That's it. Yeah. Okay. And I believe that is where we are going to stop today, because that's taking us to the metric. And we will pick up the metric tomorrow because I want a longer block of time.